All right, so this is the second part of the video. Let's look at how to find an approximate median. Okay, so far we said that if there's an algorithm that could find an approximate median quickly, then you can solve the selection problem where you want to find the kth smallest element. You can solve it pretty quickly. Okay, now so the goal of this section is to say that is to analyze. Okay, what would a random element do? Okay, so if you think about it, right, so an approximate median problem is a reasonably simple problem. So what it's asking is, I have this array A, okay, and it's unsorted, okay, and now imagine sorting it, and you got some array which is a sorted version of this. Okay. Now I want you to find some element which is in the middle n by 2. Okay. And all I want you to find is one of these elements. Okay. Now you can say, okay, what if I just start, I have the original A and I pick a uniformly random element from A. Okay. So, so that's what I'm going to analyze. Okay. So uniformly random element from A. Okay. Now, let me ask a seemingly easier question, right? Which is, let's say A prime is a sorted version of A, and I pick a uniformly random element from A prime. Okay, what's the probability that it lies in the middle half of the array, right? So if you think about this, this probability is exactly a half, right? I have it's like saying that I have this dartboard which is like a line, and I want to land in, and I throw randomly, and I have equal probability of landing anywhere, and I'm asking what's the probability of landing up in the middle half. Okay, so that would be exactly a half. Okay, and note that if I'm, as long as I'm picking something uniformly at random, doesn't matter if I picked from the sorted array or the unsorted array. Okay, so that's the reason you have that probability of picking an approximate median happens with probability equals half. Okay, so this is like a super simple algorithm, right? Like it just takes constant time. You just have to pick a random index between 1 and n. But the catch is that it doesn't always succeed. It only succeeds with a probability of a half. Okay. Now the question is, can you tell if you've succeeded or not? Okay. So that's the question, right? So can you tell if you succeeded or not? Okay. So if you think about it, yes, right? Because you tossed a coin, you found an x, which is one of the elements of the array. You can count how many numbers were less than or equal to x, and you can count how many are bigger than x. Okay, both those numbers are at least 10 by 4, then you know that you've succeeded. If even one of them is smaller, then you know that you have failed. Okay, so yes, in O of n time. Okay. So now this gives you a procedure, right? So it's like saying I have a coin, I toss it, it comes heads with probability half. It takes me O of n time to check if it's heads or not. Okay. But and now you can ask, okay, so how many times should I toss it in order to see a heads? Okay. And so this turns out to be only a constant. Okay, so this is what's called the expected value of a binomial distribution. And so this is a well-known quantity. It turns out to be a constant. Okay, so that's the whole intuition behind this thing. Okay, so I'm going to just detail the steps that I have hand waved right now. Okay, so what's the formal algorithm I'm thinking about? Okay, So I want to pick a random element. If it works out, great. Otherwise, I'm going to resample. Okay. So that's the algorithm I'm thinking about. So I call it sample and check. Okay. Pick a uniformly random element of A denoted by X. Okay. Partition the array A as elements of A less than equal to X. This thing more than X. If one of them is less than n by 4, okay, so let's have this thing, okay, if one of them is less than n by 4, then you repeat, which means you throw this x away, resample, and retry. Okay, you can also call it retry. Okay, so as stated, note that this algorithm may never stop. Okay, it's like saying that if I keep tossing coins, there is some, I mean, you can imagine that no matter how long I toss, there's some probability that I never get a heads. I mean, the probability becomes exponentially small as you take more and more steps, but there's still some non-zero chance. Okay? So as stated, this algorithm may never stop. But what I want to tell you is about the expected running time of this algorithm. Okay, so what do I mean by the expected running time? So this is a quantity that we will look at very seriously when we study randomized algorithms. We'll look at it in much more detail. But for now, what I want you to notice is that the running time of the algorithm is not deterministic, right? So it's not a fixed quantity, right? So it depends on what random choice you've made, right? So if you were unlucky, maybe you went maybe a bunch of these initial pickings were did not work out, right? So maybe they just happened to be elements that were not an approximate median. Okay, so but of course we just said that the probability of that is small. Okay, so the running time of this algorithm is not a deterministic quantity. So it's actually a random variable. Okay, so let the number of samples, sampling steps, be denoted as capital Y. It's customary to denote random variables by capital letters, so we'll do that. And so then the running time of the algorithm is exactly y times O of n, which is O of ny. So this is what we just saw, right? Like if you had to, like each of these is just O of n. Therefore, if you had to do this retrying y times, then this is exactly the running time. Okay, so that's the running time. Now, what is the expected value of this quantity? Okay, so what is the expected running time? Okay, so the running time is y times just some n. So if you knew the expected value of y, the expected running time is just O of n times that quantity. Okay, so this is equivalent to asking, so this is O of n times expected value of y. Now, how do you find the expected value of y? So this is exactly the expected number of times you've got to toss a coin so that it comes up heads. Okay, so this is exactly expected okay, and this uh, turns out to be exactly equal to 2. Okay, so the expected number of times turns out to be exactly equal to 2. in general, if you have a probability p of success, it turns out to be exactly 1 by p. Okay, so this was part of your homework 0. I'm not going to do this, but this is a very standard calculation. Okay, so if you don't know it, just look up the expected value of a binomial. Okay, so that's what this is, right? So this is the expected running time of this procedure. So even though there is some probability that it takes a long time, the expected running time is really small. Okay, and we'll see later on in the course when we look at randomized algorithms how to actually say that with very high confidence the running time is small. Okay, so those are what are called concentration bounds, and we will get to those later on in the course. Okay, so that's what I wanted to say, right? So I wanted to say that this problem of finding an approximate median, if you allow randomized algorithms, is actually very simple. And this very basic randomized algorithm of just picking random elements works in expected time O of n. And if you plug this in, remember we saw in the last video that if you plug in the running time for this approximate median oracle to be O of n, the overall running time works out to be O of n. Okay, so this gives a randomized algorithm for doing this. Okay, so in the next video, I'll show you how to do this deterministically, which is not too complicated, but it's a bit tricky. Okay, so you'll see that in the next video.